Hi guys, this is chapter 2.1. Hopefully you did the factoring practice. Hopefully you have watched the factoring video. You have to be able to factor things quite easily, fluently here and there, okay? So when you take a look at 2.1, this is talking about functions and equivalent expressions. In this chapter it talks about functions transformations. When you talk about transformations, you're dealing with one function with the same family function, not the different functions. So for example, if you have a quadratic function, you're not going to transform that to a cubic function. You're transform that to a same quadratic function, but it's either narrow or moved that way or this way, okay? So in order for us to do that, we need to be able to figure out whether the functions are in the same group. Sometimes in the graphical way it's easy to figure out, but in the algebraic way it's kind of hard to figure out. And one of the reasons and one of the key reasons is a whole. Okay, so we're gonna briefly touch upon what the whole is, and then we're gonna go move on. Okay, so the whole is one of the discontinuities. There will be three types that you will be learning in high school, and this is one of them. um, the whole in the function actually looks like a whole. Literally, it's just one whole. So if you have a graph looking like this, and if there's a hole here on the function, let's say somewhere, then all you have to do is just put a empty circle at that value, okay? And what it means is that it is indeterminate or undetermined. The reason is you're dividing 0 by 0. So whole happens at an x value, and that x value makes your numerator and the denominator 0, meaning your numerator and the denominator in the rational function we're talking have the same factor there. Then you're going to ask me, what about the other functions? Well, we're not going to deal with other functions except for the rational function and the polynomial function for now. Now, when you look at the polynomial function, it doesn't have any holes, and it cannot have it. And the reason is very simple, because it does not have a denominator, okay? Whereas the rational function, which is a function in the fraction format, has a denominator. Therefore, it can have 0 over 0 depending on the situation. So that's the first thing that we have to deal with. Now I'm going to use blue. Okay, so this is something very important, and the value that makes the factor 0 is where the whole is. So that value gives you the x value of the whole. Now then we also have to find the y value of the whole, because we need to locate where that whole is. So how we do it is then we have to simplify the expression first. Okay, we have to simplify first and then substitute that x value. Okay, so again, the first thing is x value. Then second thing is cancel or simplify. Then the third one is finding the y value by substituting. Okay, so by sub. Okay, so let's take a look at the first one. So when you take a look at the first one, it says find the whole's coordinate. So what we have to do is first, do we have a common factor here? So common factor. So common factor, do we have it? Yes, we do, right? We have x minus 3 here, we have x minus 3 there. So we have x minus 3 as the common factor. Now, the x value is the value that makes x minus 3 0. So in this case, it has to be equal to 0. Therefore, x is 3. Now, then the second step to find the whole's coordinate, we have to then cancel the x minus 3. So then we have f at x equals x plus 4 over x minus 2. Then the third step is to substitute that value into the function. So we have 3 over 4 over 3 plus 4 and 3 minus 2. That is 7 over 1. So your coordinate of the whole is basically 3 comma 7. Okay, so that's the coordinate of the whole. Now you're asking, then why are we looking for the whole? Well, you're going to see that in about a couple of minutes. Okay, let's practice how to find the whole first. Now, then the second one, we have f at x equals x squared plus 5x minus 6 over x squared plus 3x plus 2. Now, in order for you to find the whole, again, it has to be fully factored, both the numerator and the denominator. You have to be able to factor them fully, okay? So I want you to pause the video, and I want you to actually factor this. Okay, factor this numerator and the denominator fully. So pause this and then try that. So hopefully you have paused it and then try that on your own. If you don't get it, that's fine. Okay, if you don't get the same thing as I did, that's fine. You just keep trying. Okay, so if you factor this, the top becomes x plus 6 and then x minus 1 over, then the bottom becomes x plus 1 and then x plus 2. Now the thing is, do we have common factor here? X plus 6 we have in the numerator. We don't have that in the denominator. X minus 1, we have that on the numerator, but we don't have that on the denominator. So there is no common factor between, this is between, okay, b slash w, that's between numerator and denominator, right? So there is no common factor. Okay, that's what I forgot. There is no common factor. So there is no whole. Okay, so that's one. Now, so by knowing how to find the whole, we should be able to do the comparison of these two. Okay, so first let's compare the polynomial functions. So the simplest one that I can think of right now on this page is the x squared minus 4. And the other one is x minus 2, x plus 2. Now, hopefully you can notice this. X squared minus 4 is the a squared minus b squared format. So this is a difference of squares. So we can factor this as a x minus 2 and then x plus 2. Now, compare this. This, same as this? Yes. So same. Therefore, f at x equals, not g at x, h at x. So obviously when you're comparing two functions to see whether they're the same or not, they have to be in the same format. What I mean by format is they have to be either both in a factored form or expanded form or in a vertex form. So we have three forms to play around. Make sure you know how to convert from one to another. And as long as you know that, it will be quite easy for you to do with the polynomial function. Now the second one is then the rational function again. Rational function meaning a function in a fraction looking form. So if you look at f at x, we have x minus 3 over x minus 1, and then we also have x minus 6 on both numerator and the denominator. Oh, so we do have, for the f at x, we do have the common factor. So we do have a common factor of x minus 6. Right, from both denominator and the numerator. So that means that our whole's x value is 6 because x minus 6 has to be 0. Then our y value, so we simplify this. So we simplify, then we cancel x minus 6's. So your new f at x, or simplified f at x, is x minus 3 over x minus 1. Now, then all you have to do is plug the 6, which is the x value of the whole, into the f at x to find what the y value of the whole. So you have 6 minus 3 over 6 minus 1. That is 3 over 5. So your whole exists at 6 comma 3 over 5. That's your whole in the f at x. So if you look at it, the simplified version, which is the f at x, which is x minus 3 over x minus 1, and your h at x, which is also x minus 3 and x minus 1. Now this is the key moment. If I ask you to see if the f at x equals the h at x, some of you may say yes, and some of you may say no. The answer is no, and the reason is very simple. The reason is this whole. Okay, so f at x does have a whole on the graph, whereas the h at x doesn't have a whole. So if you graph this, I tried to graph this with the Desmos before, but Desmos does not show whole, so I'll just do it manually. You will learn how to do this in grade 12, so you don't have to worry about graphing this. Okay, all you have to worry about is the algebraic way. So this f at x, I'm going to draw it first. F at x has horizontal asymptote at 1, then the vertical asymptote at 1, 2, and the y-intercept is at 3, and the x-intercept is, x-intercept is at also 3. So the graph looks like this, like that. Okay. Now we know that the hole exists at 6 comma 5 over 3. So I'm going to make the axes a little longer and the graph a little longer. Okay. So we have 6 and then we have 5 over 3-ish. So it says 5 over 3 or 3 over 5? 3 over 5. So we have 3 over 5. So that's where the hole is. And this is the f at x. Okay. So these two represents the f at x. Now the g at x, sorry, the h at x is exactly the same as this, but there is no hole. So h at x is the same look, but no hole. Therefore, h at x is not the same as, not g at x, f at x. So be really careful. Before you simplify things, make sure you find where the hole is. And because of such, even though your end result, meaning your simplified version of f at x, looks the same as h at x, they are not the same. Okay, so be really careful with it. And that's why we were talking about the hole, because a hole hides inside of the function in the algebraic form. We don't know it if you actually take a look at it more carefully. So be really, really careful when you deal with such. Now then, let's take a look at the restrictions. Restrictions is another thing that you should remember of for later usage. Now, thankfully, polynomial, our most favorite function, doesn't have any restrictions. So that's a good thing. But our archenemy, the rational functions, has. So it has a hole. So that's the first thing that you have to find. Okay. Then the second thing is called the vertical asymptote. So the vertical asymptote is the value that your graph becomes extremely close, or not extremely close, but extremely high. Okay, extremely high. So in this case, the vertical asymptote is at x equals 1. That's where your graph becomes extremely high or extremely low. Okay, so that's the vertical asymptote. Now, then how do we find the vertical asymptote? Well, you try to find the x value that makes your denominator 0. And that's because the number over 0 is undefined. Now, before we say it is undefined, I can say it's a number over 0.000000000000000000001. Now, this is a number divided by extremely small number, right? I mean, the denominator number that I put is very close to 0. So sometimes we can assume that that is a 0. But actually, this is number divided by extremely small number. So this actually is number divided by extremely small number, right? Extremely small number. Now, when you have a number divided by extremely small number, that actually goes to infinity, meaning it becomes extremely large, right? Or it could go to the negative direction depending on what number you have on the numerator. So that's why the vertical asymptote exists, where the x value makes your denominator 0. But that's after you find the hole. So cancel and simplify your function, then you look at your denominator. Okay, that's where. So take a look at the first example. So here, find the restriction and determine the type of the restriction from the given functions. So A, it's a polynomial, so there is no restriction, right? There is no restriction. So that's actually good for us. Now, then B, we have a rational function. So the first thing is a hole. Okay, do we have a hole? Yes, we do, because we have the common factor from the denominator and the numerator, which is x plus 1. So I will say just there is a hole at x equals -1, because -1 is the value that makes x plus 1 0, right? Now, then what about the second one? So in order for us to find the second one, which is the vertical asymptote, we have to simplify the function. So when you simplify the function, the x plus 1, they cancel each other. So you will have x minus 1 over x minus 3. Now, is this still a fraction-looking function, meaning a rational function? Yes, it is a rational function. So you look at the denominator, and we have x minus 3. What makes x minus 3 0? Well, that is 3, right? So your vertical asymptote is at 3. Now, in case you get confused, why is it 3? Again, x minus 3 is the denominator that has to be 0 for us so that we can find what the vertical asymptote is, so equate to that 0. Then we have x equals 3. Simple, right? So hopefully you're okay with this so far. Okay, so again, when you are trying to find the restrictions for polynomial, it doesn't exist, and for the rational, it does exist. Sometimes there are two, sometimes there's one. One is a whole, and the other one is vertical asymptote. Vertical asymptote happens after you find the whole. So after you find the whole, cancel or simplify, and then find the vertical asymptote. Okay, so let's then go to the last page. So last page is basically just a practice page. So hopefully you can do this on your own quite quickly. So the first one is a rational, well, the c is a rational function. Therefore, you have the fraction. So you have the common factor here. So you have a whole. So whole is at x equals 4 over 3. Now, I'm not going to go into finding the coordinate of the whole. Okay, hopefully you can do that. If not, then let me know. Now, the second one, let's see. So we cancel things. Then we have h at x equals x plus 1. Now, this one is a linear, isn't it? This is not a rational function. So there is no vertical asymptote. Are we okay? Now, then let's take a look at g. So g the same way. If you look at it, this is a rational function, but do we have the same terms? In this case, we don't have the same terms. So no common terms, so there is no whole. Then the second thing is the vertical asymptote. So since there is no whole, we don't have to simplify anything. We just look at our denominator. So our denominator x plus 1 has to be 0, or our denominator x minus 3 has to be 0. So from the first one, we have vertical asymptote of x equals -1 and the vertical asymptote of 3. Okay, so in this case, we have a one type of restrictions, which is vertical asymptote. Oh, by the way, for the restriction, I have to go back. But you have to state it formally that x cannot be -1 or cannot be 3 because it is the value that makes the whole function a number over 0, right? So using the same notion here, x cannot be 4 over 3, okay? If you want to visit the previous one, if you go to the previous page, the second question, then obviously x cannot be 3, right? So these are the restrictions, and this is how you simply just put it. Now, then we're almost done. Domain and range is just you need to remember of. Okay, you need to remember of. Domain, we always put the set notation and say x such that x is an element of real number. And if there's a restriction, and then you put restriction here, whatever that restriction is, and then close that. And one example could be, let's say, x cannot be 3. Okay, and the same thing for the range. So the range says y such that y is an element of real number. Let's say y cannot be, I don't know, it could be 10. Okay, now then extra, this is something that we're going to discuss in class as well. This is, by the way, f at x. So f at x equals the square root of x. Hopefully you know how the function looks like. But if you try to make the table of values and try to graph this, you actually have a function looking like this. So what is the restriction in this case? What I mean by restriction here is what x value cannot be part of this function. So we're going to discuss this. Now, this is your homework. So please complete the homework, okay? So I'll see you guys tomorrow in lunch. Thanks for watching. Bye, guys.